My name is Dan Pipp. I'm a Direct Image Specialist with Geoprobe Systems. This training video is going to cover the gas phase detectors that are commonly used within the membrane interface probe system. We want to talk about their operating principles, the type of compounds that they can detect. We'll highlight the features within the detectors that will allow the operators to be able to be successful at mapping anywhere from sub-part per million levels to NAPL level of VOCs. We will also discuss the compound list and some detection limits that are probably achievable within the system. And then we'll go and review some logs. And within the log review, we're going to look at the various detectors, how they are each responding, and what we can discern about the contaminants based on the detector responses. So if you're ready, let's begin. There are various brands of gas chromatographs, or GCs, used to house the gas phase detectors used in MIP, but probably the most common one is the SRI, which is in the photo in the lower right corner. There are three detectors that are most commonly used together, and they are the XSD, FID, and PID as shown in the photo above the GC. Before we look at these in more detail, we will describe the operation of collecting the sample, which is analyzed by the MIP detector. The membrane interface probe is advanced into unconsolidated soils by the use of a direct push machine at approximately 1 foot intervals. The advancement is stopped to allow for samples to diffuse across the membrane. The membrane is housed on a heated block on the side of a probe which reaches temperatures of approximately 120 degrees Celsius. This elevated temperature enhances the ability of volatile contaminants to diffuse across the membrane into a carrier gas stream that continually delivers the analytes to the uphole detectors. The first detector that the analytes are exposed to is the photoionization detector, or PID, which is non-destructive. The PID contains a UV lamp that continually exposes the carrier gas to its high-energy UV light source. When compounds are present whose ionization potential, IP, is below that of the PID lamp energy, which is typically 10.6 electron volts, they are ionized. These ions are then drawn to the collector electrode, which produces a current that is proportional to its mass. The current is amplified and recorded as signal by the instrumentation. Analytes that are commonly detected by the PID are aromatic hydrocarbons and certain chlorinated solvents, displayed here by benzene and TCE. Both of these compounds contain carbon double bonds and have an IP that is below that of the lamp excitation energy. Hydrocarbons and chlorinated solvents without carbon double bonds typically have higher IPs and cannot be detected by the PID. Example compounds are butane and 1,1,2-TCA. The next detector we will review is the FID, or flame ionization detector. It is a destructive detector and contains a hydrogen flame. As analytes are combusted, positive ions are produced which are drawn to the negatively charged collector electrode. Here a current is produced proportional to the mass of carbon, then amplified and displayed as signal by the instrumentation. The FID is the least sensitive of the detectors, however it is able to detect any carbon-based compound if in high enough concentration. All VOCs are carbon-based, thus detectable by the FID. The next detector is the halogen-specific detector, or XSD. It operates at extremely high temperatures, typically 1100 degrees Celsius, which naturally results in it being a destructive detector. The compounds are broken down into their oxidative products and free halogen atoms. Inside the detector cell, there is a platinum electrode, which the free halogen atoms are attracted to. Once absorbed to the cathode, a current is produced, which is amplified and results in a signal within the instruments. The XSD uses oxygen to encourage the oxidative process, and the response of the XSD is flow rate dependent. The lower the flow, the better the signal, as there is more time for the analytes to absorb to the cathode surface. As the name states, it is a halogen-specific detector, meaning that only compounds with fluorine, chlorine, and bromine will respond. It will not respond to petroleum hydrocarbons. Given that most environmental impacts are chlorinated, the XSD produces similar responses to a wide range of molecules regardless of the number of chlorine atoms on the molecule or their structure. As responses increase at the detectors within the MIP system, we will not be able to stop and perform dilutions as would be done in a laboratory. We need to be able to use the features of the detectors to be able to see from part per billion range levels to as much as free product. Each detector system has individual signal output limits. On the SRI, the PID and FID can output a signal up to 5 volts. The XSD can output up to 1 volt signal. The detector can see beyond that, however, the system cannot output that signal and it will result in a flat line as we see here on the FID. To report above these levels, we must change the gain setting on the detector, or the GC, and the attenuation setting in the software. Adjusting the gain will divide the signal down so that the detector can output the full signal, and the software attenuation factor will multiply the response back up to scale in the software. Here is what a response of 40 ppm TCE looks like on the PID and XSD at each gain level with appropriate attenuation factors. This was also done on the FID using butane. Again, we see each gain level is producing a similar overall signal response. We're going to show the gain attenuation changes for each detector on this particular system. As the gain level increases, we do see a baseline shift or a little bit of increased noise with the current concentrations being sampled in this test. But if it's needed in the field, it won't be noticeable as the concentrations are going to be significantly higher. Here is a list of some of the compounds that may be commonly mapped in the field using MIP. This list is not all-inclusive and has been derived from the EPA 8021 compound list. It shows important molecular properties as well as which detector they would be detected by. A more expanded list is available on our website. Here we have example detection limits for each detector, with the first number being what a well-maintained and performing system should be capable of detecting in standard MIP mode. Detection limits are commonly defined as detector signal 3 times over the baseline noise. Keep in mind that detection limits should be checked and determined for each particular unit working on a site, as detection limits are influenced by system wear and maintenance upkeep. Now let's interpret some logs. Here we have a similar patterned response on the PID and XSD. Since the XSD is responding, we know it must be halogenated, and with the PID providing a similar pattern, it must be double bonded, and its ionization potential must be below the excitation of the lamp. We likely have a PCE or daughter product plume. Since we also see significant response on the FID, which is not mirrored on the PID, because it's too high of an ionization potential, or the XSD, it's non-halogenated, it's likely due to the presence of methane. This log shows similar response patterns on the PID and FID without any response on the XSD. No response on the XSD means it is not halogenated. With similar PID and FID responses, it is most likely petroleum hydrocarbons. Other contaminants that would respond like this would include MTBE and ketones such as acetone or methylethyl ketone, which may be included in some aerosols. Now we will look at a couple of low-level MIP logs. Don't let the spikes fool you, just focus on the patterns displayed by the detectors above any background that may be present. Here in the top 10 feet, we see similar PID-FID responses without any XSD, so it's likely petroleum hydrocarbons. Below 25 feet, the pattern changes, and the PID and XSD show a similar pattern. Here we have a halogenated double-bonded compound, perhaps PCE or TCE. In this example, once again, we have surface PID-FID responses without any XSD response, likely petroleum hydrocarbons. Once we reach 35 feet below grade, the XSD shows 2 separate responses, neither of which are mirrored on the PID. It must be halogenated, but the ionization potential must be higher than the lamp energy, so it's likely a single bonded chlorinated, which I believe here we had 1,2-DCA carbon tetrachloride and chloroform, which was confirmed by groundwater samples sent to the lab. While MIP cannot tell specific compounds or exact concentrations, quite a bit of information about the contaminants can be discerned from the logs using your knowledge of the detectors.